kids to McDonald's, just have some family time.
Sounds pretty nice.
What about you?
Yeah, I went to Hawaii. It was warm, and I can just lay on the beach.
Kind of like what we're doing here, you know? Just
Yeah.
Oh shoot, here comes Kabir.
Hey, what are you guys doing over here?
Just a lot of break times.
I don't see any work being done. So where's you guys in hard hats? Where's your vest? No protection over here?
I kind of forgot it today. I don't have it.
What's all this material laying around in the puddle? You guys are running all the material. How are you going to use this? It's all wet.
That's all the scope of my expertise, personally.
This is strong enough. Mostly the structure now, the this is what's important science there. I'm going to prove it's going to be so strong now.
Alright, you got 3 days to prove it to me.
Sure.
Hey Reshad, did you figure out the max load that we can columns can handle?
Yes. So our demand was 35 kids, correct?
Yes.
So back when I was back in college, when I was taking structure lab with Professor Matsumoto, so this is what I learned from his class. We have this specimen.
Just give it to him. It's okay.
Okay. So we measured its dimensions. It came up 3.5 by 3.5. From here we can easily calculate its area. So we multiply, it's going to be 12.25 inch square. For our specimen, first thing is we have to do is we have to measure its water content with our tools. As we measured, it came up 12%. And we, using the maximum allowable stress equation, we can easily predict the maximum load it can handle. So this is the equation for maximum allowable stress. So from here, if we take out the maximum load it can handle, so we calculate for maximum load. So it's going to be maximum allowable stress times the area. The maximum allowable stress value we get from our wood handbook from chapter 5. So it's going to be 7,430 psi. Using this value and our area, so we multiply, we get 91.02 kips. So this is the maximum load our structure can handle, our dry specimen.
What about, the wood we left out in the rain a little bit?
Yes, so here, I calculated for that one too. So for our the width, for our width specimen, we measure with our tools its water content. So it was 24%. From here we can use the same equations we use for our dry specimen to get our maximum load. So before that we have to get our maximum allowable stress for water content of 24%. So we can get that from our wood handbook, chapter 5 as well. So as we get it, it came up 3,870 psi. So this is again our equation for maximum allowable stress. This is maximum load divided by the area, and we can easily calculate for maximum load. So it will be maximum stress times area again. So we have values we get from our wood handbook, and our area we calculated, our area of the specimen. So we multiply, and it's gonna be 47.41 kibs. So this is the maximum load when it's applied on our structure, our structure will fail. As we see here, our demand was 35 kibs, and our maximum load we predicted is greater than the demand. So we're totally fine using the wood specimen.
Honestly, I'm just upset that Kabir even made us do this. He should have trusted that we knew what we were doing anyway. I don't know. I'm just gonna go tell him about this right now. Elliott,
Okay.
you should get over your fear of him. You're gonna come too.
Okay, thank you guys. Oh. Thank you.
All right, Kabir, we figured it out. We did the numbers, and we sorted out that's gonna be fine. So for if it was a dry specimen, as in we didn't get the wood wet, it would be 91 kibs would be fine, and which is like way more than our demand of 35. So we also did the calcs for the wet ones. It was not a big deal. It was 47.4 kibs that it can handle. Again, that's way higher than demand. It's
Okay,
fine.
it's nice that you did the calcs, but do they make sense?
Well, we did them.
Okay, now go prove it. Go to the lab setting and check if your predictions are actually true.
Seriously?
Yeah.
All right, fine. Come on. Glad that went well. I mean, it was kind of a toss-up how it's gonna. Oh, hey, Kabir.
Hey, you guys called me?
Yeah, we wanted just to show you the results of the lab test you wanted us to do. So I don't know if you want to have a seat.
Let's see what you guys got.
Great. So what we did is we took two pieces to the lab, one dry and one wet. The wet one was saturated by submerging it in water for 36 hours, and the dry was just left as is. We went ahead and checked the moisture content with a gauge before going ahead and testing it under axial compression, as shown here in the load cell. And we made sure that they were both the same dimensions. So they were both 3.5 by 3.5 inches by 8 inches height. First, we went ahead and tested the dry specimen, and what we found was this pretty cool crushing failure. As you can see here, and there's this like really nice split through here. And so that's what we did first. We went ahead and took our saturated specimen, which is right here, and we checked the moisture content again for both right before I went into the load cell, just to make sure it's where we were going to have the right numbers. And for this it was 24%, the dry was 12%, and as you can see we also had this really cool just crushing failure here with this like really interesting split. And we also went ahead and dyed it blue, just because we were hoping to be able to see how far the water might have saturated into the specimen. It didn't really take the color, unfortunately, but we thought that was a nice idea to try. So we went ahead and plotted that data just to be able to show you more specifically what happened. And in our plot, we went ahead and on our y-axis gave you the compressive loading that we applied and the displacement that came forth from that. So in red is our dry wood specimen and its behavior. We saw that the max load it was able to withstand before failure was 62 kibs. The deflection there was 0.0983 inches as shown. And in blue is our saturated woods behavior. And as you can see, we actually hit this really high mark of 55.98 kips. And the deflection there was 0.1045 inches.
Okay, that's fine and all, but why are these results different from what you had predicted?
Elliott, do you want to go ahead?
Sorry guys, I was looking for more wood. So in our predicted versus actual results, in the dry wood, our predicted was 91 kips, while our actual was 62, which is an actual to predicted ratio of 0.68, which is much lower than what we expected. However, the mode of failure was still crushing, and failed in compression and it crushed. In our saturated piece of wood, which was 24% moisture content, our predicted strength was about 47, while actual strength was almost 56, which is a actual to predicted ratio of 1.18, which means that our saturated wood is actually stronger than what we have predicted. And our mode of failure was we had a nice crushing split. So if we look at the test results on the dry piece of wood, you can see there's an existing crack, which would have weakened the strength, and then it crushed. There's no nice split. You have some failures at the bottom and the top, which could have been due to how it was loaded. There's a crack going diagonally this way and multiple failures. While the crack that was marked right here, it didn't fail at that point. You can see it expanded from what it originally was. Now in our saturated piece of wood, there's a nice Y-shaped crack and split. So it's split right down the middle. You can see it go right here. So this is a more ideal type of failure, which means that in practice, this is actually how it would fail, ideally. If you look at this actual wood specimen, there's some existing cracks which greatly reduce the strength of column, and then if we turn it, there's knots throughout the wood. Since it's a natural piece of wood, there's a lot more natural defects, and knots greatly reduce the strength. In addition to, if we look at the top, there's a knot here, which could reduce the strength as well. And so it is very difficult to predict the actual, to get ideal failure of wood, since there are so many different factors that go into testing.
Guys, everything checks out. Looks like we can continue with the project, but next time wear a hard hat.
But what about wood rot?